Welcome back everyone. In the previous video we solved theory of computations questions that were asked in June 2019 NET exam. So today we will solve questions that were asked in December 2019 exam, and there were 10 questions from theory of computation. So let us see what is our first question. Which one of the following options is correct? L1 equals to context-free language. L1 is representing context-free language. L2 is context-sensitive languages. L3 recursively enumerable languages, and L4 is recursive languages. So now what are our options? Option A is L1 is a subset of L2, which is further subset of L3 and L4. So all we have to do is we have to find relationship between all these languages. So this one is quite easy. We all know that if we make a diagram for these, it will be like if we make a diagram for all these, it will be like in innermost circle it will be context free languages. We are representing them as CFL. Then there will be context sensitive languages in the outer loop. It is CSL, context sensitive languages. Then we have recursive languages. So I'm representing recursive languages as RL. And then we have recursive enumerable languages. So it will be REL. So this is the relationship between all these languages. So we can say that CFL is a subset of CSL, which is further a subset of RL, which is further a subset of REL. So our right relationship will be L1 is a subset of L2, that is context sensitive language. Then it will be a subset of recursive languages, which are represented using L4. So it will be L4, and then we have recursively enumerable languages, that is L3. So if you see our options, option C is our right answer. Our next question is, consider the language L equals to a raised to the power n, b raised to the power n minus 3, such that n is greater than 2. This is our condition. On alphabets A and B, which one of the following grammars generates the language L? Okay, in options we have 4 grammars, and we have to tell among these 4 grammars which one will generate this language L, where a raised to the power n into b raised to the power n minus 3. Whenever we encounter these types of questions, best approach is to find lowest or smallest string from each grammar. So if we consider option A, let us find what will be our smallest string. Here we are given S gives AA and S gives small a. So small a will be our smallest string or word from this grammar. So smallest word will be small a, right? Now if we see our question, our condition is n should be greater than 2. So minimum value of n can be 3, right? So if we put 3 in this language, that is a raised to the power n, b raised to the power n minus 3, and if we are taking n equals to 3, it will be a raised to the power 3 into b raised to the power 3 minus 3, that is 0. So it will be a cube, right? But smallest string from option A is single a. So option A cannot be our right answer. So we will just cross it. Let us see what is our second option. Second option says S gives small a in and capital A. Second, S gives lambda. Lambda means empty string. So smallest string from this grammar will be empty string, that is lambda. But from our question, we know that smallest string from our language is a cube. So again, of S gives small a. So smallest string from this grammar will be, so again option C cannot be a right answer. So by using elimination method, we know that our right answer will be option D. For the sake of knowledge, let us see how it is our right answer. It's and one capital A, right? Now we have a single non-terminal variable, that is A, and we can replace this A with either small a, capital A, B, or lambda. Let us replace this A with lambda. If we are replacing A with lambda, so smallest string will be triple A. So this is exactly what we required. Answer because it gives as our language. Now let us see one more string. Suppose we are replacing this A, small a, capital A, B, right? And initially we have triple A. Now this capital A can be replaced with lambda, that is our empty string. We will just ignore it. So at the end, our next string or our next word will be A raised to the power 4B. Now this is, if we put n equals to 4 in our to the power n, we will replace n with 4, n minus 3, that is 4 minus 3, we will get A raised to the power 4B. That is same as we just derived. And you can take few more examples and you will see that you are getting exactly those words 3. So our right answer will be option D. Our next question is, which of the following is correct with respect to the following grammars? Now in this question, we are given 4 grammars, and what we have to do, our option A is G1 and G3 are equivalent, G2 and G3 are equivalent, G2 and G4 are equivalent. So basically we need to find among these 4 grammars which one are equivalent. Equivalent means they have same number of words in that language, plus they have exactly same words. So again we will try to find smallest string in each grammar. So let us take grammar G1. It says S gives alpha SB, S gives B S alpha, and S gives alpha alpha. Just pause the video, take out your pen and paper, find smallest string among these 4. Find smallest string from all these grammars and you will get your answer. So for G1, smallest string will be alpha alpha, right? Now for G2, if you just said, it says S gives alpha SB, S gives BS alpha, S gives SS, S gives lambda. So smallest string will be lambda, that is empty string, right? For G3, its smallest string will be alpha. Just pause the video, do it yourself. And for G4, its smallest string is lambda. Now we know the smallest string from all these grammars, and you can see that G1 and G3 have alpha, alpha and alpha respectively as smallest string. So it is very clear that G1 and G3 are not equivalent to any other grammar. So we will just ignore G1 and G3. Now we have to check whether G2 and G4 equivalent, because smallest string from both these grammars is lambda, right? Now all we need to do is check few strings from G2 and G4. We know that smallest string is lambda. Now there is one more method to see this. It is quite direct method. Just see, first production is alpha SB from first production in both these grammars is alpha SB. It is same. Second production is BS alpha. Again it is same, so we do not need to check it. Now third production is SS. It is again same. And fourth production in G4 is triple S, which is missing in G2. So all we need to check whether we can find this production, that is SSS in G2. Okay. Now see, in G2, we are talking about G2. In G2, we have S gives SS, double S, right? Now we can replace this S again with SS. And let us take it as it is. So we can drive this production, that is S gives triple S in G2 also. Okay. Rest productions are same. The only difference was triple S was present in G4. But we can drive this production in G2 as well. So we can say that G2 and G4 are equivalent. So right answer for this question will be option C, that is G2 and G4 are equivalent. Our next question is, consider alphabets W and X and T equals to XYZ. Define homomorphism H by. Now we are given two functions for homomorphism. First is h of x equals to xzy. Second is h of w equals to zxyy. If L is the regular grammar denoted by R equals to W plus X clean closure, WW clean closure, then the regular language HL is given by. Now see, we are given a regular language, one regular expression is given, and we have to find homomorphic expression for same regular language. So we just need to apply homomorphic functions on this regular language, on this regular expression. So this one is quite easy. We are given two homomorphic function. One is on X and one is on W. So our first alphabet in regular expression is W. So we will replace this W with h of W. Now what is h of W? This is our second homomorphic function, that is x, that is z, x, y, y. Done. Then we have plus symbol, just put it. Next we have x clean closure. Now we will replace this x with homomorphic function of x, that is our first function, h of x equals to x, z, y. So we will replace this x with x, z, y, then clean closure of this x, z, y. Done. So we will put it inside the bracket. Next we have w. Now again we will replace this w with h of w, that is z, x, y, y. Again we have w. Again replace this w with same string, that is z, x, y, y. Then just put clean closure outside this bracket. So this will be our right answer, that is regular expression for h of L. And if you consider all these options, you can see that this will be matched with option B. So right answer for this question will be B. Next is, this one is very interesting question. Which language does this grammar generate? We are given a grammar and we have to tell what will be the language for this grammar. Okay, so what we have, S gives 0A or S gives 0BB. Next, A gives 0A, A gives 00A, A gives lambda, B gives 1B, B gives 11C, C gives B. Now what we are doing, we are just segregating this grammar in two portions. One is S gives 0A. So basically we are dividing this language on the basis of its terminal. So basically we are dividing this language on the basis of non-terminals. First we are taking A as non-terminal. So we are writing all productions that involves A, right? We have only 3 productions that involves A in it. Next we will write all productions that does not involve A. So it will be S gives 0BB. Then it will be B gives 1B. Next will be B gives 11C. And last will be C gives B, right? Okay, let us consider productions involving A first. Now here it says S gives 0A. So 0 will always be there in our language. Next we have A. Now we can replace this A with either 00A or lambda, right? So if we replace this A with lambda, then we will at least get a 0 in our language. So we can say that smallest string from this grammar, that is S gives 0A, A gives 00A, and A gives lambda. So smallest string from this grammar will be 0, right? Next, let us say we are replacing this A with 00A. Now again we are getting A. So we can see that A gives 00A. In this we have self loop, right? So self loop will be like 0, that is our smallest string. Then we have 00, and we can repeat this 0 0 as many times as we want. So it will be 0 into 0 0 closer. So is that clear? From this grammar we can derive this language which says 0, that is at least we will get a 0, then 0 0 clean closer. Clean closer, why is it so? Because smallest string from this grammar will be 0 only. Okay, then we can have 0 0 0, then we can have 0 0 0 0 0. Okay, so we will get odd number of zeros. Now let us see what will be our language if we are considering grammar that is written on right hand side. If you notice this grammar, you can see that there is not a single production with terminal on right hand side only. This grammar will never reach its final state. Okay, so we will not consider this, we will consider only grammar involving A as non-terminal. So right answer for this question will be 0 0 0 clean closer, and if you consider all the options, you can see that our right option will be option C. Okay, if you have any doubt, you can ask in comment section and we will try to respond as soon as possible. Next question is, which of the following statement is or are correct? Okay, one important point, this question has been asked in July 2018 NET exam also. Exactly same question was there, so that is why it is important to solve previous year's questions. Okay, what is statement first? There exists no algorithm for deciding if any two Turing machines M1 and M2 accept the same language. Now this statement is true. Why is it so? Because it is standard equivalence problem and it is undecidable. That is why no algorithm is there for deciding if any two Turing machines accept the same language. Now let us see what is statement number 2. Let M1 and M2 be arbitrary Turing machines. The problem to determine language of M1 is a subset of language of M2 is undecidable. Again, this is true because it is standard halting problem of Turing machine. It is undecidable. So both these statements are true. So right answer will be option C. Both S1 and S2 are true. Next question is, which one of the following is correct? L equals to n raised to the power n, b raised to the power n, where n is greater than equals to 0. Okay, this is our language given in the question. Statement 1 is, L square is context-free language. Now let us see what will be L square. L square will be L into L, right? So it will be a raised to the power n, b raised to the power n into a raised to the power n, b raised to the power n for n greater than equals to 0. And this language L square is context-free language because we can easily design the push-down automata which accept this language. Okay, so statement S1 is true. Statement 2 is L raised to the power k is context-free language for any given k greater than equals to 1. Now again this is true. Why is it so? If you do remember, in previous video we discussed some important points regarding all languages, and in context-free language we know that context-free language is closed under clean closure. So basically L clean closure is our context-free language if L is our context-free language. Okay, so using this property we can say that L raised to the power k will be context-free language. So statement 2 is also true. Statement 3 is L complement and L clean closure are context-free language. Now we already know that context-free language is closed under clean closure. So L star will be context-free language. Now let us check what about complement of L. Now we know that context-free language is not closed under complement. Okay. But here we have a particular case, that is a raised to the power n, b raised to the power n. Now what will be the complement of a raised to the power n, b raised to the power n? Complement of this language will be language accepting all strings other than a raised to the power n, b raised to the power n. Okay, that will be the complement of this language. And we can easily design a push down automata which rejects a raised to the power n, b raised to the power n and accept all strings other than these strings. So again, L complement will be context-free language. So all these three statements are true. So right answer will be option D. Okay. Next is, which one of the following is or are inherently ambiguous language? L1 is a raised to the power n, b raised to the power n, c raised to the power m. Union a raised to the power n, b raised to the power m, c raised to the power m, where n and m greater than equals to 0. Now this language L1 is inherently ambiguous language because we cannot have any unambiguous grammar for this language. And we can find proof for this statement in Ullmann textbook. So L1 is inherently ambiguous language. Now what about L2? L2 is W reverse, okay, where W belongs to A and B. L2 is not inherently ambiguous language, and one unambiguous grammar for this language is S gives ASA, S gives BSB. Now this question has been asked many times whether WWR is inherently ambiguous or not. And this is not inherently ambiguous because we can represent it as using this unambiguous grammar. You can easily verify that this one is unambiguous language. Okay, so among L1 and L2, only L1 is inherently ambiguous language, L2 is not. So answer will be option A, that is only L1. Next is, let G equals to V, T, S, P be any context-free grammar without any lambda production or unit production. Let K be the maximum number of symbols on the right side of any production in B. K is maximum number of symbols on right side. The maximum number of production rules for any equivalent grammar in CNF, that is Chomsky normal form, is given by. Now we are given K as maximum number of symbols. We have to find maximum number of production rules. Our first option is K minus 1 into number of production rules plus number of terminals minus 1. Next option is K minus 1 into number of production rules plus number of terminals. Option C is K into number of production rules plus number of terminals minus 1, and last will be K into P plus T. So right answer for this question is option B, that is K minus 1. That means maximum number of symbols on right side minus 1 into number of production rules plus number of terminal. Now this question is asked directly from Peter Lynch textbook. This is very famous textbook of theory of computation, that is Peter Lynch. Okay, so always to remember, its right answer will be option B. Next is, this one is very interesting question. Let A equals to 001, 0011, 11, 101 and B equals to, there are some strings. Similarly, let's see, in this we have 3 strings and in D again we have 3 strings. Now our question is, which of the following pairs have a post correspondence solution, that is PCP solution? Okay, we are given 2 pairs, A and B and C and D. Now among these we have to tell which one has PCP solution. Now our question should be how to find PCP solution. So let us take A and B first. Now we have A and B. Okay, let us say we are representing index for both these A and B as 1, 2, 3, 4. Now what is PCP solution? We have to find some combination corresponding to these index such that that combination is equivalent for both A and B. For example, in this pair of A and B, we have one PCP solution and that will be 3, 4, 1. What does it mean? This one is 3, that is index number 3. Then we have index 4 and this one is index 1. Now we will write A3, A4 and A1. See the sequence, we are using same sequence 3, 4, 1. Now what is A3? A3 is 1, 1. So we will write 1, 1. What is A4? It is 1, 0, 1. And what is A1? It is 0, 0, 1. Again we will follow same index sequence, that is 3, 4, 1 for B also. So it will be B3, B4 and B1. So just write strings corresponding to this sequence. B3 is 1, 1, 1. So we will write 1, 1, 1. B4 is 0, 1, 0. And last we have 0, 1.